again, and welcome again to the Hannover Messe Hydrogen Fuel Cells Batteries Group exhibit. This is our last talk for the day, and I'm happy to welcome Jessica Elwell, who is the program manager at Ceramatec, Inc. Thank you very much for joining us, as well as, hi, good to see you, thank you. As well, we also have Dr. Werner Schulmeyer, head of solid oxide fuel cell innovations services at Plansee. Thank you for joining us as well.
Hi.
Thank you, hi, welcome. So first of all, these are two different companies, so I would like to get, if I could get a little bit of information about your separate companies, please, to share with us.
My name is Jessica Elwell. I work with Ceramatec, which is a subsidiary of CoreStech. We focus on research and development of solid oxide ionic materials. My group is specifically in fuel cells and fuel processing.
Thank you very much. And for yourself?
Yeah, my name is Werner Schulmeyer. I'm a member of the Plansee group. We are a large producer of metallurgically produced metals. This is mainly molybdenum and tungsten. And within the Plansee group, there are 4 divisions. The one I belong to is the High Performance Materials division. And in there, we have all of the activities for SOFC. And I'm heading these activities. And that was the bridge or the link to the company of Ceramatec. Yeah.
Fantastic. And at this point, I will mention again the title of our conversation today. All the acronyms. It's called A Journey to Mars, O2-generation by electrolyte-supported cells-based solid oxide electrolyzer cell stack with Plansee's and CFY's interconnects. Whew. It's a mouthful.
Good job.
Thank you. Could you please speak about to your design considerations?
Sure. So what we did was we designed a stack based on NASA's requirements to participate in the Mars 2020 rover. So we were given a very specific weight allocation, volume allocation, power requirements. To operate the fuel cell, we require an entire day's worth of power from the rover. So we had to make sure that we were mass constrained, we were volume constrained. We also had to survive launch, entry, descent, and landing. So we had many considerations as far as the structural integrity of the stack. As was mentioned, it's an electrolyte-supported cell. So we had a lot of design considerations that led us towards the cooperation with Plansee to make a very specific interconnect design.
Thank you. Anything else that you'd like to add at this moment?
No.
Not quite yet? Okay. And could you please give us a bit of background, Jessica, again, on the mission?
Sure. So MOXIE, which is the Mars Oxygen in Situ Resource Utilization Experiment, or obviously MOXIE, is the one of 7 experiments that were chosen to go aboard the Mars 2020 rover, which is a Curiosity-class rover. The experiment itself is to do a demonstration of in situ resource utilization. The atmosphere of Mars is 96% CO2, so the system will take the CO2 and electrochemically convert it to carbon monoxide and oxygen. For this mission, the oxygen will just be vented to the atmosphere, but first they'll do some characterization on it. Overall, with a $2.1 billion mission, there's a lot of quality considerations. We built stacks to aerospace flight standards, which was a challenge for a research company. But yeah.
If you'd like to elaborate a little bit more, please feel free. I know you're very passionate about this mission, about this project. Both of you are. So please.
Okay, so let's see. Where am I? The overall mission itself, so it will take the launch is considered to be for July or August of 2020. It was a really interesting project for us because usually we do a lot of research projects for industrial firms or for the US government where you can get extensions if you have some struggles within the program. On this one, if you did not finish your tasks and meet your criteria by the time of launch, then you are done. You just don't get, your ticket is canceled. So we had a very tight timeline, which drove our design forward very quickly. So it was really integral for us to have a team like we had with Plansee, where the feedback was immediate and we were able to advance the design really rapidly. I think
Thank you. And so for you, this is the first of hopefully many collaborations that you will have with Ceramatec. How did the collaboration come about? You gave a little bit of it at the beginning, but if you could go more into depth.
It actually started with a joint contact that we have. One of our customers, the company Hexis, was in touch with Ceramatec. And via this route, they got knowledge about our special alloy, the CFY alloy. It's a chromium-based alloy. And the key feature of that is that it has a special coefficient of thermal expansion, which exactly matches the requirements that Ceramatec had for development of this MOXIE SOEC stack. And via this joint contact, we got into contact with Ceramatec. And at the beginning, we are sure that we have the right material and the right experience and expertise, but we were really challenged with the time frame. And another challenge really was there was no specification. We got presented a rough estimate about where we should go to, but it was always moving targets. And this, under the time pressure, was a real challenge. But as we had known Ceramatec a little bit before already, we had the real strong feeling that in cooperation with Ceramatec, this is possible to handle. So we said, yes, we will enter into this project, and in hindsight, it's been really rewarding. But in the beginning, it took some guts to step in.
Of course, saying, oh, did we make the right decision? Is this the right way to go? But fantastic that it's worked out. And as far as for you, for Ceramatec, what are sort of the any challenges that stand out in your mind?
So we, like was just said, the requirements for this program were a little bit drifting. It's an experiment, so NASA put forth multiple requirements regarding purity, operational cycling. As I said, the system's power constrained, so we have our heritage design would have 100 degrees C per hour heat up ramp. This will have 90 minute heat up from whatever ambient is, which on the surface of Mars can be negative 40 C, to our operating temperature of 800 C. So we have a 90-minute heat up, we have a 120-minute operational cycle, and then we shut off. And then it's a couple days, and the rover moves around some, and then we turn it back on again. So we had a lot of challenges as far as material sets, which I'm assuming people in the crowd have some electrolysis, at least knowledge, and understand where that goes. But so we did these rapid operational cycles. We had to maintain thermal cycles. JPL took a stack down to negative 40 C, then cycled it down to negative 55 C, then down to negative 65 C, and we tested this afterwards operationally. No change in O2 purity, no change in performance. So we've really overcome some pretty impressive challenges. Another major challenge, as I mentioned, was the structural integrity of the stack itself. In JPL testing, JPL did, the Jet Propulsion Laboratory did the systems packaging. The heaters for this system, the way we do it is in a hot box in our test lab. The heaters for this system will be integrated on the top and the bottom only and heated through the stack, and then there's an insulation and compression packaging around it. So the stack had to withstand pretty high compressive forces without cracking the electrolyte so that we would have a leakage. The seals had to withstand the same. We went through multi-axis vibrational testing, and we also went through multi-axis shock testing, where they mounted the system to a beam and then launched a projectile at the beam and then sent it back to us and said, does it still work? And it did. So no change in purity, insignificant change in performance. So we were really excited about some of the major accomplishments that came out of this. So, and another, at least I think, interesting point to that is, as we've been saying, there was a really tight timeline for development. We went from undergoing the contract with NASA to the design phase of the interconnect to our first stack test in 6 months. So that is the full production of the interconnect, all of the coatings, everything developed 6 months from making our first CAD sketch of what the interconnect part would look like to a stack. Then, not surprisingly, we found some challenges with that. The first one leaked a lot. We had 1 week to develop the seal. So over the next few months, we address this. We are approximately 2 years into the program. We passed flight qualification in February, which means after the 20 operational cycles expected by NASA, we're still above their 99.6% oxygen purity requirement. We're still producing more than the 6 gram per hour requirement with a 55 gram per hour feed rate of CO2. And I mean, we've launched projectiles at it. So it's a raging success for Ceramatec. It's been a really fun development project. Critical to the entire design was the collaboration with Plansee. We're really excited about where this is and what we really were able to accomplish in such a short amount of time.
Thank you. At this time, I'd like to see if anyone has any questions for either company. Not yet. I will, at the end, I'll mention the, oh, is there a question? No? Yes? Okay, I'll come to you. Thank you.
Hello. As far as I understood, heat up and operation is done completely electric.
Correct.
I'm interested, what is the electric consumption of the operation and the heat up? So
the stack itself operates at 50 watts. This is the entire system. I think I failed to mention that this is a 0.5% prototype. So a manned mission would have 200x. I won't hold it when it's that size. But so we have a 90-minute heat up. I, off the top of my head, can't remember the power consumption on heat up. But the operation itself, this is a 50-watt stack.
Okay, any other questions from anyone else? Sorry. Then we'll come back. What would you say, what differs your products from other ones in the market, even similar ones?
So with what we've done here, I think people in the industry can appreciate that. Normally you wouldn't feed dry CO2 to an electrolysis stack. That wouldn't really be a terrestrial application of choice. So we had some really interesting materials challenges where we tweaked the actual cell chemistry so that we had a coking resistant cell, that we got rid of anode delamination. So we have a very stable cell that can operate through all of these pretty intense thermal cycles and different testing. Another thing that came out of this project was the fact that we have such a rugged stack design. We learned a lot in this design overall that we're now working towards scaling up to a commercial terrestrial application for either hydrogen or syngas production or potentially for SOFC as well.
And we did learn a lot as well. I mean, to build a stack, there's a lot of joining technology into it, and this is we have I think a very much fitting setup at our headquarters in Reutte. There was a lot of development, and it's not designing the flow channels and the interconnect itself. We did a lot of work on the joining technologies. We made quite some experience in a short time, and this is possible at our headquarters because we are linked to many labs. We have an undestructive testing. We can do joining technologies. So overall, we had 2 major iteration phases. The one was 6 months to create the demonstrator for first testing, and then a second go-around to apply improvements. And it has been really challenging, but we stepped in because we know we have the background and the setup at a headquarters. But maybe after all, there were many humans involved, and we certainly had many times during the project where it really was a touchy item to lay open where are the limits and to take some risk, to be proactive, and maybe instead of only 2 variations to produce 3, to have a kind of a backup without making a new contract. And this was a mutual trust that was developed during the project, and it helped really and gave us a boost to be confident to achieve the goals. And as NASA has passed it, and obviously the parts will really fly, that's what we see from today's point of view, I think this was a real key. We had a lucky setup, but there were a lot of human positive factor into the thing.
A lot of hard work.
That's great, and congratulations on getting the project. What would you like, just to sort of on a closing note, for people to take away from this conversation today, as far as your project and your success and so on? partnership?
Ceramatec is now in the flight build cycle. As I mentioned, we passed flight qualification of all of our processes and materials. So we're building the stacks that now we'll build 11 stacks, and they'll pick the lucky one that will go to Mars. The Jet Propulsion Laboratory is doing the Mars ambient testing, where they have a vacuum chamber. Mars atmosphere is 7 millibar, so they're doing a lot of the testing regarding operation, integration with the pump that will feed the stack, the measurement systems that will tell us what the oxygen purity are. Those types of activities are underway. Ceramatec fully supports the mechanical development of the packaging system. We have members on their board of advisors for that activity. And then at Ceramatec ourselves, we're moving towards having a commercial project. We've been doing R&D for about 30 years on solid oxide fuel cells. And with everything we've learned here and some other projects, which I would love to talk about if anybody wants to, I'm in booth 38 _2.
I will mention that again at the end to make sure.
Okay, just thought I'd throw it out there.
Thank you,
That we've really come to a point where we're really confident in our material set. We've addressed a lot of really tough challenges for this technology, and so we're in the process of scaling up. And in doing so, we recognize that Ceramatec's heritage view towards a research-centric organization didn't fit as well with what our next steps would be. So Ceramatec formed what we're calling Oxyon Energy. I've probably talked to some of you about it today. And we will take this through a scale-up where we'll partner with Plansee for the new interconnect design for the scaled-up option. We're also doing some design work towards the next phase of the Mars mission, which they'll scale up the oxygen plant. So Ceramatec will again, Oxyon I should say, will again compete for that contract. But we feel very confident with what we've accomplished. We have a happy customer, which I don't think is always easy in space.
And for yourself, any closing notes?
Yeah, and we were rewarded in joining this project with having two real nice opportunities. Like Jessica mentioned, there might be a follow-up project, the MOXIE 2 project, which will be then a scale-up. And this project will not end in high volumes, but we learn a lot. And the second branch that has opened up is the new startup of Ceramatec. And within the Plansee group, we already have large customers. One of them is Bloom Energy, buying at high numbers from us their interconnects. And of course, we are hoping, along with Ceramatec, to develop new customers at that size, and that's a real chance. And no matter what happens, we are already rewarded. And so we are looking very positive to the co-work with Ceramatec, or Oxyon Energy.
Both
That's
are
the new name.
Well, again, congratulations on your successful project. And you are in booth number
38-2.
38/2.
With steelhead composites. So you won't find me on a program, but
It is just behind us here. And so again, our thank you to Jessica Elwell, Program Manager from Ceramatec Inc., and as well our thanks to Dr. Werner Schulmeyer, Head of Solid Oxide Fuel Cell Innovation Services at Plansee.
Yeah.
Thanks again.
Thank you.
Thank you.
Thank you.
Thank you.
Thanks. Thank you very much for joining us today, and we will see you again tomorrow at 10 a.m. Have a good evening.